So now the next question that we want to answer is, what do you do if you have more compute budget, right? So suppose you are given 4x more compute budget, right? Then what do you do? Do you train on more data, right? Or do you increase the size of the model, right? Because if you increase the size from x to 2x to 4x, then the number of computations that are going to happen in the model will increase, and then maybe that the new compute that you have, you could use to scale up this compute, right? So you are going to have, you have compute for 2 days. In one setup you have some say access to x compute for 2 days. In another setup you have access to 4x compute for 2 days, right? So now if you use a larger model, a 4 times model roughly, then that 4x compute running for 2 days could give you the same 4x compute running for 2 days would be able to handle this model, as opposed to when you had only x compute, then you could not have used a larger model, right? So should you increase the model, go from a BERT base like model to a BERT large like model by increasing the either the D model size or the feed forward network or the number of layers or the number of attention layers, right? There are many various ways in which you could increase, but you would increase in such a way that the total computation or the total number of parameters either ways becomes roughly 4 times, because you have 4 times more compute, right? Or you could say that I'm going to build only 4 models, each of them is going to be of size x only, but I'm going to use an ensemble. So now instead of training one model, I can train 4 different models because I have 4 times the compute, and then I'm just going to use an ensemble of these 4 models that I have. Or I could just train for longer, right? So instead of t is equal to 2 raised to 19, I could train it for 40 steps, right? So now can I train for longer? Or I could increase the batch size, right? Because now if I increase the batch size, every batch has more 4 times the number of tokens that I was seeing earlier, hence 4 times the compute will be used. So that is also a possibility. All of these are options. So what should you do, right? So they tried all of this. This was the baseline. Then they use the model size the same, which is 1x, but they use 4 times more training steps, right? So if they were using 2 raised to 19 steps earlier, they're using 4 into 2 raised to 19 steps now. The other thing that there was, okay, train it for 2 raised to 19 steps also, but each step is now a bit bigger, right? Or it packs in more data. So it packs in 4 times more data per step, right? So if your original step size was 128, sorry, original batch size was 128, now you can use a batch size of 5 and 2, right? So each batch you're doing more, right? Each step you're doing more. And so increasing the batch size led to better performance, you can see, across all the tasks, right? And in some cases quite a bit of jump, as you can see. Okay, the next thing you could do is keep the model size to something but increase the number of training steps. So they did 2x the model size and 2 times the training steps, or 4 times the model size and the same number of training steps. Again, in both cases you can see an improvement over the baseline, right? So having a larger model or having a larger model and training for longer steps, right? Having a larger model but training for the same number of steps, that's the last row. Or having a moderate side model, which is 2x times the original model, and then training for a moderate number of steps, is both of these are leading to better performance than the baseline, right? Then they also tried the ensemble, and the ensemble also seems to do well, right? But all of this says that if you use a larger model, train it for longer, that seems to be a win-win situation, right? You get more bang for the buck by putting it more compute, right? So that's the end of all the studies, and the main thing here was whether we want to scale the number of parameters, not scaling parameters, but scaling the number of parameters or training steps. And there is a trade-off we need to make here, because if you scale the number of parameters, then you need more compute during fine-tuning the model also, right? Because right now we are only talking about pre-training, but when you are fine-tuning, again you have a larger model to deal with, so you'll need more time at fine-tuning also. And of course, when you deploy the model, because it's a bigger model, you will also have a larger inference time, right? So that is a trade-off you need to make, but this table at least suggests that larger model trained for larger time steps actually helps, right? So that's sort of an end of all the studies that they did, and based on that they came up with the following model, right? So architecture is encoder-decoder. Objective function is denoising with span corruption. You remember those experiments that they had done where they tried different objective functions and denoising was the best and the span corruption objective was the best. Then pre-training, the cleaner corpus C4, which is a filtered version of the common call corpus, that is what they use. Training strategies, so multitask pre-training is what they did, right? Because there was not much difference between unsupervised pre-training and multitask pre-training, so they just added all the tasks to pre-training. Model size bigger the better, so they are going to try multiple model sizes, and training steps longer the better, right? So they train models of different sizes, starting with a base model of 60 million, going all the way up to an 11 billion model, right? And if you look at the base model, which is, sorry, the small model, which is 60 million, it has 6 layers. The 11 billion model had 24 layers. Then the D model size was 512, here it was 1024, and the feed forward network size, here it was 2048, whereas here it was 65536, right? And this is, I think, the number of, I don't know what DKV is. Yeah, the size of the KV embeddings that you get, and the heads, right? So the number of heads was also much larger in this case, right? So generally just use a bigger model, the first row versus the last row, and just scale up all the parameters that are there in the model, right? All the dimension sizes that are there in the model, right? And we also know that training for a longer number of steps or larger number of steps and using a larger batch size helps. So that's what they did. They trained all the models for roughly 1 million steps with the batch size of 2048, right? Remember, in our experiments, we are looking at batch sizes of 128, 256, 5 and 2. So they used a batch size finally of 2048, right? So you are training for longer number of steps or larger number of steps, and each step is also like a very power packed step because it is looking at 2048 tokens per step, right? So they did all the best practices that they could do, and this corresponds to the model seeing a total of 1 trillion tokens, right? So 2 raised to 20 multiplied by 2 raised to 11, and that is 32 times higher than the baseline model that we were experimenting with throughout, right? And of course, all of this should lead to best performance. So indeed that is, so whatever was the previous best at that time, of course now all of these numbers would have been beaten by much bigger models and better techniques and so on. But at that time, whatever was the previous best, they were able to significantly beat that, not maybe significantly, but at least on some tasks have a good margin. And except for the machine translation tasks, right, where it was clear that you would have the best performance when you have a supervised approach which just deals with translation, right? So these best models are not necessarily the same model, right? It is whatever model gave the best performance on that task. So for example, it's not that all of these are results from BERT base or BERT large or from BART or from GPT-2, right? These are all from different models, whereas T5 as a single model was able to give better performance on various tasks and not drop drastically on some of the other tasks, right? Okay. And as you scale the number of parameters, you get a better performance, right? So that's all. So we have looked at the T5 model in quite a bit of detail. So in our journey, we have finished the encoder models, which was BERT, and in combination with that, we looked at the tokenizers. Then we did the encoder, decoder only models, which was GPT and GPT-2, and we looked at decoding strategies in combination with that. And today we did encoder decoder models, where we looked at BART and T5, and we looked at a lot of things in sort of combination with it. We looked at different factors which matter for performance. We looked at different objective functions, different ways of scaling the model, all of that, and finally arrived at the configuration for the T5 model, which was an encoder decoder model. So I'll end this video here, and I'll see you in the next lecture, where we'll talk about, now that we have a basic understanding of these three families, what are the other models in these three families, and then how do we differentiate between these models. Thank you.